Okay, let's use hybridization to describe the bonding and structure in propene, which has a formula of C3H6. You want to start by looking at the Lewis dot structure here. So each carbon brings with it 4 valence electrons, each hydrogen brings 1. The underlying skeleton, then, shown here, has a total of 18 electrons in the valence shell that we need to put into the molecule. We can start adding them pairwise between each set of atoms that are bonded. It's a total of 8 bonds for 16 electrons, leaving a pair of electrons left over. If we add that to the 2 carbons on the left, what we get is a carbon-carbon double bond. This gives 8 electrons around each of the carbons in propene. The line skeleton drawing for propene looks then like this. And if we start by considering these 2 central carbons, we recognize that because there is a double bond, these are sp2 hybridized carbons. The bonding in between them then consists of a sigma bond and what you can think of as a pi bond. Now, the geometry around these carbons, these sp2 hybridized carbons, is necessarily trigonal planar. There are bond angles of 120 degrees, roughly, in the carbon-hydrogen to carbon-carbon or other carbon-carbon bonds. And the other consequence of having that pi bond in between the 2 carbons is not just the bond angles, but the fact that there's no rotation around that carbon-carbon bond. So that carbon skeleton is coplanar, and there's a barrier to rotation because rotating around that bond would involve necessarily breaking the overlap between the p orbitals that are forming the pi bond. The carbon on the right of propene, on the other hand, is sp3 hybridized. It's got 4 separate sets of electrons coming off of it. The geometry that we associate with sp3 hybridization is that it's tetrahedral, and now, unlike the carbon-carbon double bond, the carbon-carbon bond right here is freely rotating because it's just a sigma bond. All the electron density is localized directly in between those 2 carbon atoms, and so you can freely rotate without disrupting the overlap between the bonding orbitals.